Good day, and welcome to the June Pacific Northwest Drought Early Warning System Drought and Climate Outlook webinar. My name is Morgan Lawrence, and I'm with the Northwest Climate Hub. This bi-monthly webinar series is hosted by the National Integrated Drought Information System, the USDA Northwest Climate Hub, and the Oregon Climate Change Research Institute. It is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar is tailored to reflect recent, current, and forecasted conditions in climatic events, but also includes discussions of observed impacts and other relevant updates from across the region. Webinars, recordings, and other supporting materials will be posted on drought.gov later this week. Just a note that after today's webinar, you will have the opportunity to provide feedback that will help us improve this webinar series, so please take a moment and tell us what you think. So the agenda today, today's speakers include Karen Bumbacco from the Office of the Washington State Climatologist at the University of Washington with the climate recap and current conditions. We'll then hear from Ed Townsend with the National Weather Service Forecast Office in Pendleton, Oregon, about seasonal conditions and water supply outlook. Then we'll hear from Matthew Kazuda with Oregon State University about the weakened orographic influence on cool season precipitation and simulations of future warming over the western U.S. Finally, we'll get a demo of the newly expanded drought.gov state pages with Kelsey Satolino from NOAA, NIDIS, and CU Boulder. We will be using the Q&A box at the right side of your screen for questions during the presentations, and we'll address those and additional questions during the Q&A period after the 4 presentations. Before we begin the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based, region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. Visit the website listed for more information. The Oregon Climate Change Research Institute is a network of dozens of researchers at Oregon's public universities that work closely with other public and private entities. OCRE is housed at Oregon State University. OCRE advances understanding of regional climate, impacts, and adaptation, and cultivates climate-informed communities. NIDIS was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional drought early warning systems, where networks of partners and stakeholders share information and actions that help communities cope with drought. While the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across the regions. Each DEWS has many of the same base ingredients, but ultimately have their own flavor to reflect the needs of their region. The Pacific Northwest Drought Early Warning System was officially launched in February 2016, and our strategic plan and information on current activities is available on drought.gov. To facilitate our early warning system, more precipitation observations are needed. We encourage you to join COCORAS, the Community Collaborative Rain, Hail, and Snow Network. This is a unique, nonprofit, community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, rain, hail, and snow, as well as condition reporting. Observations by COCORAS observers of precipitation events and the lack of precipitation are important events to capture and improve our understanding of weather. To become a volunteer or to learn more, visit cocoras.org or contact your state coordinator. Names and emails will be placed in the chat box. So now we will turn it over to Karen Bumbacco.
Great, thanks, Morgan. Does that look okay?
For some reason, Karen, it's not showing up now that we've tested it. Let me try.
I'm seeing it.
There, it did it. Hold on, sorry. Let me give it to you again. It looked like it just was slow popping in.
How's that?
That looks great. Thank you.
Okay, great. All right, well, good morning, everyone. My name's Karen Bombacco. I am with the Office of the Washington State Climatologist, and lots to update on the Pacific Northwest today, so I'll get right into it. This is taking a look at our water year temperatures and precipitation. So this is going back to October 1st of 2022, just through a couple days ago, so through the end, sort of the end of June. And what we can see is that we've been much cooler than normal for most of the Pacific Northwest for the water year as a whole. Averaged for each individual state for just October through the full month of May, we had below normal temperatures averaged over Idaho, Montana, the whole state, not just Western Montana, and Oregon. So some pretty big anomalies on the water year scale there of almost 1.5 to 2 degrees Fahrenheit below normal. But temperatures were near normal in Washington, and that is because the warmer temperatures west of the Cascades sort of evened out the slightly cooler temperatures east of the Cascades. And then lots of spatial variability in temperature with Washington, Northwest Oregon, the Panhandle of Idaho, and the northern part of Western Montana drier than normal, and then wetter than normal anomalies in the other parts of those states. So I wanted to highlight February through April. This was cold again throughout the entire Pacific Northwest. Anomalies much larger than what we were seeing for just the water year. So those anomalies are listed there on the left-hand side. Rankings, Oregon and Idaho were both the 13th coldest February through April on record. These records are long, they go back to 1895. Washington, not as high on the rankings from cold to warm, but the 31st coldest. Montana averaged across the state the 35th coldest. So really a cool spring that we've had. Temperature was definitely, again, more mixed across the region, still seeing a very similar signal. We're drier on the northern regions of the Pacific Northwest and wetter on the southern regions of the Pacific Northwest. Montana and Washington were averaged more on the drier side with 84% of normal precipitation averaged over Montana, 87% of normal for Washington. And then Oregon and Idaho were on the wetter side, but when you average across those states, they were more near normal for the February through April precipitation there. But the last 60 days, we really saw a drastic switch in that temperature signal. So this is going back just to the end of that previous period, April 22nd through June 20th there, just the last 60 days. We can see how warm it's been across the region. For Washington State as a whole, just the month of May tied 1958 as the warmest on record, so over 5 degrees Fahrenheit above normal for the state. Similar anomalies across Montana, Oregon, and Idaho, all ranked as the 5th warmest for their records. So really warm. Precipitation, the most notable record here for the month of May was Washington, and that ranked as the 15th driest. But note this sort of strange signal in precipitation where southeastern Oregon saw above normal precipitation for this period, which is sort of odd considering our weather patterns. So I looked back at the atmospheric circulation. This is showing the sort of middle part of the lower part of the atmosphere, so mid-troposphere, and those the circulation patterns for that same time period, so April 22nd through June 21st. And what we're seeing here is an anomalous easterly flow pattern. So you have that anomalous easterly flow aloft that brought that precipitation to kind of the southern part of the Pacific Northwest on the eastern flank of the Cascades and then along southern Idaho. But the heights were high enough in the northern part, so over Washington and the Panhandle of Idaho, to suppress that precipitation. So sort of a strange pattern that showed up in our precipitation there. But anyway, back to the warm temperatures in May. So we had a really rapid loss of our snowpack because of how warm those anomalies were. On the left-hand side, all of those red dots, these are our snow-till sites in the mountains, so measure of our snow. And the red dots show that they had the largest snow water equivalent loss at that individual station for the month of May, shown here. For Washington, that translated into, well, I should say Washington and the northern part of Idaho and western Montana, that translated into a lot of sites that melted out earlier than usual. An example on the upper right here from the middle of the Washington Cascades, that black trace is our snow water equivalent building throughout the season. And you can see that it peaked in late April for Washington State at this specific site. And when we went into our warm May, that snow melted really quickly, and it ended up melting a few weeks early at that site in Washington. That did happen in Oregon as well, but not as much because Oregon had such a great snowpack this past year. This is an example from central Oregon Cascades here at New Crescent Lake. They had such above normal snowpack here that warm May did still cause a rapid loss of that snow melt, but the snow still melted out later than usual. So the usual is this green median line on these plots here. So it's been an interesting spring. As far as our reservoirs go, I guess I'll start with the bad news first. On the upper left-hand side here, these are our 5 main reservoirs in the Yakima Basin in Washington. This blue trace is the current storage in those reservoirs. You can see that it's been below average, this red line here, for most of the water year. We've been on the dry side, especially in Washington. They were rapidly refilled in May with our snow melt, so got up to normal here in mid-May, but then they're starting to drop below normal for the basins there, the reservoirs in Yakima Basin. So the Bureau of Reclamation for Yakima released a mid-June forecast, and they are projecting that the junior water users will only receive about 73% of their normal entitlements for the rest of the water year. On the other hand, the water storage in Oregon is looking really good with both the big snowpack and then also that recent precipitation, especially in southeastern Oregon. The Willamette Basin reservoirs are trending lower, though, due to the drier conditions that we've seen recently, and then the fact that a lot of their reservoirs are actually dependent on rain rather than snow. However, there's not really any concerns at this point for the Willamette water system for this current water year, but the potential for decreased carryover into an El Nino year next winter, which I'm sure we'll hear more about from Ed, is somewhat worrying for next year. The only other problem that my colleagues in Oregon told me to mention is the low reservoir levels on the Wickiup, which is shown here in central Oregon that feeds the Deschutes Basin. There is concern that with the dry soils as well in much of that watershed, that irrigation demand will be high and may not be fully met throughout the summer because those reservoirs are also on the lower side. So the last 30 days, that pattern has continued in terms of warmer than normal temperatures. There has been some moderating in western Washington and northwest Oregon with a little bit of a cool week we had recently with actually a little bit of precipitation too. But overall, that period has still been much drier than normal and split across the northwest in this diagonal line. Whoa, okay. Sorry, that jumped around quickly there. But this is where I'm supposed to be. So this is just showing that pattern in our stream flow. So on the left-hand side is the average stream flow over the month of May. So all those green and blue dots are showing normal to above normal stream flow, and especially on our snow-dominated rivers, we really saw high flow because of the quick melting from the snowpack. But even in the rain-dominated rivers, most of them were normal throughout the Pacific Northwest in May. But then in contrast, the right-hand side shows just the last 14 days of the average stream flow. So showing that it's really dropped, particularly in the rain-dominated streams in western Washington and northwest Oregon. We also see some reds popping up in northern Idaho and Montana. I did want to note some stuff we're hearing here from Washington. Some drought impacts are starting to emerge for western Washington. So the junior water users in the Skagit Basin, which is sort of here in Washington, are already on curtailments, and that is earlier than what usually happens in the summer. And then Nia Bay, which is where the Makah tribe is here on the way tip of the northwestern part of Washington, is already on water conservation and have also had some hatchery fish that have had to be relocated due to low flows already for this time of year. Soil moisture, this is very much showing the pattern of precipitation that we've seen really all water year and more recently in terms of the drier root zone soil moisture here. This is from NASA GRACE. And then the USDA topsoil moisture map is showing Oregon and Washington agricultural lands at 65% and 70% of the topsoil being short to very short. And this is recently from the week ending on June 18th. This demonstrates that the irrigation demand may be higher this summer despite the good to great snowpack throughout the Pacific Northwest. So we are watching this closely as well. So in terms of the changes to the Drought Monitor map, this has closely followed what we have seen in terms of our weather patterns. So some worsening happening in the drier parts of the region and some improvements happening where it's been wetter. This is the current map here, and I'm going to go quickly now because I think I'm very close to the end of my time. And here are just my summary points, which I'll leave up on screen so we make sure we have time for our other presenters. And I thank you for your time.
Thank you, Karen. I don't see any questions yet, so we'll go ahead and go on to our next presenter. And that looks great.
Thanks, Brett. Hello, everyone. My name's Ed Townsend. I'm the Science and Operations Officer at National Weather Service Pendleton. I'll be discussing the current conditions as of date, provide our outlook for the summer, and give the latest on the El Niño Southern Oscillation, or ENSO. I'll provide spoilers and get the key points up front. Looking at our snowpack for this water year and what we're coming out of, most of the Oregon Mountains, Southern Washington Cascades, and Idaho Mountains saw average to above average snow water equivalent this winter. Of note, the situation wasn't as promising up in Washington and parts of northern Idaho where snow melted out early and they had not as much snow water equivalent stored. Provide a look at the 18-48-day outlook where it's warm and dry, though small tilt towards being wet in eastern Idaho. Looking ahead this summer, warm and equal chances for below near or average precipitation this July, August, and September. Looking at drought, it looks like drought will persist where it's currently present with drought development likely across western Washington and northwest Oregon. Fire danger is above normal with significant fire potential present across Washington and much of Oregon and Idaho, except for parts of southwest and northeast Oregon and in the east in Idaho. And El Niño. Right now, El Niño is observed with these conditions expected to continue throughout winter 2023-2024. This graphic shows our snowpack, snow water equivalent peak as a percentage of the average over the 1991 to 2020 period. Looking at our snow telemetry or snow tell sites over the Pacific Northwest, much of the Pacific Northwest this winter saw peaks of 90 to 150% and higher relative to the historical peak snow water equivalent. That said, there were 23 snowtail sites with less than 90% as a percentage of their average peak, and those are kind of donated in that yellow color. And they're greatly found across most of central northern Washington and parts of far western Montana. In terms of snowpack onset this year, while not shown, snow actually occurred earlier than normal, with a lot of our sites seeing onset frequently around 1 to 3 weeks early. and that could be attributed to the active weather that occurred a week before Halloween and that weather in early November. Looking at how we melted out, this visual shows this year's snowpack meltout date compared to the average calculated meltout date. And this illustrates where our Pacific Northwest snowmelt sites stood when it came to melt. Green to blue colors indicate sites where meltout occurred later than normal. Orange to red indicates sites where meltout occurred earlier than normal. And this kind of piggybacks off what Karen showed, where we see Washington, parts of northern Idaho and western Montana saw sites that really melted out up to 1 to 4 weeks earlier. Meantime, compared to across much of Oregon, it was well maintained a little later on into the season. Now, before we get to the water supplies, here is a review of the seasonal precipitation on the left for the water year as a whole through mid-June, and that's comprised of rain and melted snowfall. Water year precip is largely near normal to above normal across southeastern Oregon through southern Idaho. However, we can see a patchwork of near normal seasonal precipitation across far western Washington, northwest Oregon, and eastern Washington. Areas of below normal precipitation were common across much of eastern Oregon and across areas of and near the Cascades. Looking at the Northwest River Forecast Center's water supply forecasts on the right, you can see that median forecast shown here as a percent of the 30-year normal, which shows the above average conditions at site across much of Oregon. In other words, these forecasts that are highlighted in the colors of cool, blue, green, and darker shades of blue speak to the wetter side relative to past outcomes over that April to September time period. Of note, the much higher water supply forecasts are seen across Harney, Malheur, and Baker counties in Oregon. Drier forecasts and a corresponding lower percent of normal can be seen across the northern two-thirds of Washington, extending into Canada. And this is consistent with what the situation that was illustrated by Karen when it comes to Washington State and their reservoir levels. Continuing to look at this from a climatological perspective, we can see these wetter and higher median forecasts position well when we look at percentiles and past values. So this shows the percentile of the historical record equal to or less than that average forecast that was previously shown. Looking at these water supply forecasts across Washington over that April to September time period in the northern two-thirds, we can see that forecast falling very low in connection with climatology, or that, in other words, corresponding percentile of that historical record. Looking at the 10th percentile when it comes to that forecast in some sites near Yakima and near Ellensburg and higher across the north central Washington. Keeping in mind, we're now moving into our drier months of July through September. Switching gears, here's the 8 to 14 day outlook from the Climate Prediction Center, or CPC. Odds favor above normal temperatures with a large area of 50 to 60% seen across the Pacific Northwest. That is, the observed temperature is likely to be above normal, and with the 8 to 14 day outlook, we're talking about the average of the mean temperature of all those days in the period. The 8 to 14 day outlook for precip doesn't show as much of a strong signal. We do see a slight or small tilt in the odds, greater than 33%, but not really more than 40% west to east, of which odds are just leaning into that below and above normal categories across western Washington and Oregon to eastern Idaho, respectively. Elsewhere, we do see parts of Washington and northeast Oregon do have a small tilt in the middle category or near normal precipitation. Here's our July outlook. This shows Pacific Northwest largely dominated by equal chances, and that is an equal chance of the odds tilting in any direction, and there's not a single direction being favored when it comes to above normal, below normal. Note for the monthly and 3-month outlook, again, it's covering all those days in the period. So doesn't mean we're not going to see above normal temperatures or below normal temperatures at any point. Just the summary of it is equal chances. We do see a slight tilt in the odds for above normal temperatures along the Pacific Northwest coast, and we also see above average precipitation across eastern Idaho and parts of western Montana. Kind of peeking ahead, even though we have an El Niño advisory, the influence isn't really strong when it comes to these seasonal and monthly outlooks in the summertime for the Pacific Northwest. And that could be kind of attributed to that uncertainty in the forecast amongst the different tools and guidance. Going into July, August, September, There is a modest tilt above 50% for much of Oregon and much of Washington, with decreasing odds going eastward into western Montana. When it comes to precip, equal chances is in place across much of the area again, except for western Washington, northeast Oregon, or northwest Oregon, and parts of western Idaho. This area of equal chances is considered to have odds that are similar to climatological probabilities, and when we're seeing this equal chances for precip, there isn't much of a climate signal to favor one outcome more than the other. And this really speaks to the difficulty in the forecast as we get into this summer time frame, as per we just came out of that spring barrier. So the guidance and tools get a little better, but there's still some uncertainty. Meantime, above normal chances are favored when it comes to temperature. Drought. The latest Climate Prediction Center drought outlook shows droughts persisting. We're currently present across central Oregon, portions of northeast Oregon and northeast Washington, and much of northern Idaho. Outlook does call for likely drought development across a large area of western Washington and northwest Oregon. And for reference, there is the latest United States Drought Monitor on the left. Note there are some minor differences or agreement between these two, and there are some differences stemming from when these forecasts are released between the seasonal drought outlook and the drought monitor. Keeping in mind the previous monthly and seasonal forecasts that showed those odds that were higher and favored warmer than normal conditions and a tilt towards below normal precipitation, especially across the Pacific Northwest coast where we're expecting that drought development that is likely to occur. The National Interagency Coordination Center and local predictive services do come together and provide a significant wildland fire potential outlook. While there is a subtle change between July and August, the theme is the same July onwards. Above normal significant fire potential is present across Washington and much of Oregon and Idaho. Normal wildland fire risk is still present though, and it's not to say that we're not going to get fires. It's just that normal risk, which is generally, that is to say low, there's still that risk of wildland fire, but there is that above normal risk across this area that is just displayed in red on these two maps for July and August. And this potential in part could be attributed to those likely above normal temperatures and the dry weather that is expected. Changing gears and turning to climate patterns, let's look at where we sit with respect to ENSO, or El Nino Southern Oscillation, which is a major climate driver that can influence temperature or precipitation. With the one caveat is every location sensitivity and the amount of influence from ENSO varies, of which usually climate impacts with ENSO are most reliable during winter in the US, and that includes the Pacific Northwest as well, where the effects of El Nino are somewhat weak during the summer. So I do want that to be somewhat of a preamble for the slides ahead. Right now, El Nino conditions are observed, and we are seeing warmer than normal sea surface temperatures across the monitoring area of East Central and the Eastern Pacific Ocean. Going forward, it is increasingly more likely than not for El Nino to continue and to strengthen into this upcoming winter and through this upcoming winter. There's even chances for a moderate strength El Nino event this winter, where probabilities are right now at 80% based on the latest information from the Climate Prediction Center. The table on the left shows the recent state of ENSO the last 13 years, and as you can tell, in 2021 through 2023, we just had our triple dip La Niña, and we can see now we do have a positive value of 0.1 for that 3-month period of March to May on this Oceanic Nino Index, which is our main tool for assessing Niño and La Niña episodes. And that really is centered on that Nino 3.4 region, which is kind of on the graphic on the right at the bottom, which also shows the other regions that are being monitored when it comes to sea surface temperature departures, or that difference from normal. On the right, we do have this visual that shows the sea surface temperature departures or anomalies across those different monitored areas. And we can see that Nino 3.4 region, again, is the primary one used, has been increasing as we've gone through April, May, and June. So again, we are in an El Nino right now, and we're expecting it to continue. Not to discuss El Nino too much, this is the official Climate Prediction Center ENSO probabilities. Very high, exceeding 90% for El Nino going forward with the continuation through this upcoming winter. last slide. This shows El Nino composite maps revolving around the summer timeframe. On the left is the percent of average precip over the June to August summer season, when there was El Nino, of which we have 29 events. On the right is the number of summers when we had a El Nino, but with above average precip. This mainly goes to show how much variability there is when it comes to the range of possible outcomes with El Nino in the summer. Parts of Central Oregon to South Central Washington and Southern and Eastern Idaho were near normal to slightly above average with El Nino. And you look at the frequency, we can see 15 counts in these areas where over half the El Nino events had above average precipitation. So if we place the frequency of El Nino events side by side with above average precip, it does reveal a number of events with El Nino that were wetter than average across the summer. And here's a repeat of the key points, and I will pause now if there's any questions or if we're going forward.
Great, thank you both. We do have one question that came in. Perhaps this is for you, Karen. When eastern Umatilla County, Blue Mountains, and higher plateaus received rain, it was from intense thunderstorms, which were deluge-like. Yet we are below average for rain in the past 60 days. Can you explain the disparity?
Yeah, sorry, I'm here. I was looking back at the 60-day map. So I'm still seeing above normal on the 60 days. So I'm not sure what exact disparity is.
Okay, maybe I'll put you in touch with the person asking the questions, and we can, share some of the products, et cetera, and find some resolution to the question if that works for you.
Yep, that'd be great.
Awesome. Great. Well, thank you, Ed and Karen, our first two speakers. And at this point, I will turn it over to Matthew. For our next presentation.
Alrighty. Alrighty, look good to you?
Looks good, thank you.
Great. So yeah, my talk today is weakened orographic influence on cool season precipitation and simulations of future warming over the western US. I'm a graduate student, a PhD student at Oregon State University, and this is part of my dissertation work. And it's currently being revised for resubmission to geophysical research letters. As many of you I imagine would know, a lot of our cool season precipitation in the western US comes from frontal systems and atmospheric rivers. When these intersect mountains on the western coast, orographic precipitation is formed where this moist air is forced to ascend, leading to enhanced condensation and precipitation to form. On the windward side of the mountain, where most of this precipitation falls, it leads to a lot of the water supply in the western US, and across the world, over 50% of people rely on mountains for their water supply. As the air goes over the mountain into the lee, it's no longer supported by the terrain below, causing it to descend, warm up, and evaporate some of that precipitation away, leading to precipitation minimums. And this is defines the rain shadow in mountain ranges, which is the focus of my talk today. When we look at climate model simulations of future climate, we can see in global climate models, which are relatively coarse on the left, that the mountains are not usually represented adequately to get this orographic precipitation adequately represented when compared to regional climate models on the right, which are much higher resolution. You see total precipitation that's more realistic and in line with what we expect in our simulations. And this is the reason why we do regional climate simulations. The same can be said for what we term the precipitation sensitivity, which written out here in these terms represents the percent change in precipitation scaled by the local temperature change. And in the mountain lee, where the rain shadow exists, we see much larger values in the precipitation sensitivity in future climates And it only shows up in these higher resolution simulations. This is a pattern that has been shown in numerous studies of regional climate models, with increases in the relative terms in the lee of mountains versus the windward regions. And this implies a weakening of the rain shadow. And so in my talk today, I'm going to present a set of PGW simulations that were run and the results from that, and then propose a simple model to represent this precipitation sensitivity pattern that we see. And we'll show that our model does a good job of emulating the actual pattern of precipitation sensitivity, which we term as alpha. So the PGW simulations that we run try to answer the question, how would a historical weather event been affected by a warmer climate? We do this with a control simulation using reanalysis data in the WRF modeling framework at high resolution. And we did it for a period of 30 years. And then the PGW simulation takes that same historical boundary conditions, but adds a monthly mean perturbation of temperature, winds, and moisture that are diagnosed from these coarser GCM simulations. You can see them listed here, and they were found using the RCP 8.5 emission scenario, the worst case scenario, the business as usual scenario. And that's basically a fingerprint of climate change that's added to the historical simulations. So just to note, the WRF simulations do a good job representing the historical pattern of precipitation. If you compare it to an observational product like PRISM on the right here, you can see a very similar distribution of highs and lows in precipitation, although there are some biases across the Mountain West. The pattern of precipitation change in our PGW simulations is pretty uniform across the Western US, with some exceptions along the Western US coast, shown here, where there's larger increases in precipitation in some of the windward regions of the Cascades and Sierra Nevada mountains, but it's also interspersed with decreases in precipitation as well. And this is for the ensemble average of those 5 GCM simulations we used. And if we look at the precipitation sensitivity, which I had shown before, we see these much larger increases in the lee compared to the windward regions of the Cascades and Sierra Nevada mountains. But it's also present in some of these coastal ranges, the Olympic Mountains and the Rocky Mountains as well. This is all showing a pattern of rain shadow weakening. And so today I'm going to show a simple model that we developed to explain this. We start by separating total precipitation into a large scale component and a mountain scale component. And then from our PGW simulations, we show that there's a relationship between how sensitive large scale precipitation is compared to orographic scale precipitation, which leads to this pattern of total precipitation shown here. To do this, we use, to get the large scale component, we use a 2D Gaussian filter applied here on this change in temperature pattern for the ensemble average. The filter width is approximately 1,000 kilometers, so it's really trying to get the large scale effect. And that's what it looks like on the right when we apply this smoothing filter. We do the same from the total precipitation field here on the left to get the pattern of large scale precipitation here in the middle, using that same Gaussian filter. And when we remove the large scale pattern of precipitation from the total precipitation, the residual gives us the orographic scale precipitation, or that mountain scale precipitation, which is shown here on the right. Regions that are blue are positive, showing enhancement of the large scale precipitation forced by the mesoscale, the orographic features of the underlying mountains. And then on the right is the areas that are negative in the lee, where the mountains suppress precipitation, leading to that rain shadow. And so this separation is the foundation of our model. And we start with that separation here. And I don't show this, the math where we work out the total equation, but we also will assume that each component of precipitation will be sensitive to warming at different rates. So we have a alpha orographic and alpha large scale term here. But our final equation that we get is alpha equals alpha large scale minus this fraction of orographic precipitation to total, and then the difference between these two precipitation sensitivities. Our large scale precipitation sensitivity for the ensemble is shown here in the middle. It's relatively uniform across the Western US between maybe 2 to 5% per Kelvin. And then we can also diagnose this fractional term from our simulations. And it's shown here on the right, and we designate it as this F value. The only thing that we can't solve for from our simulations explicitly is the alpha orographic value. If we try to calculate it explicitly from our simulations, the F, that fractional term in the denominator, cause it to doesn't behave well in getting a value for alpha orographic. And so we take a point in the Western US and we try to minimize the predicted value of alpha from the actual value of alpha for different values of the orographic precipitation sensitivity term in this circular region. And we do this across a numerous subsample of points in the Western US to get a total relationship. And when we do that, we get this relationship where large scale precipitation is more sensitive than orographic scale precipitation. And we come to this conclusion since most of the points fall below the 1-to-1 line, meaning that the large scale term is larger. And it's the linear relationship that comes from this. If we assume it's a constant offset of 3.1%, that gives us the best fit for this data. And so this term here, alpha large scale minus alpha orographic, represents a diminished influence of mountains on our precipitation field. And we plug it into our equation here. You might ask, why does this relationship exist? And I'm not going to go into too much details here, but people have proposed, for example, Sheen Duran, that mountain wave dynamics play an important role in future orographic precipitation change. But in two regions in our simulations, they show different mountain wave responses to warming, with increased vertical velocities in the Sierra Nevadas and decreased in the Cascades of Washington. But if you recall, they both show similar precipitation sensitivity plots. And so we focused on a thermodynamic mechanism due to condensation being more sensitive to warming higher in the atmosphere. And there's a difference in how orographic ascent is structured in the atmosphere compared to large scale ascent. And I don't want to get into the details for this talk. I don't really have time for that. And so in our paper, we show this theoretical argument more clearly. But the difference between the large scale and orographic scale precipitation sensitivity are approximately the same as our empirical evidence from our PGW simulations. And when we apply our model to our PGW simulations, the simple model here, we get this approximate pattern of precipitation sensitivity on the right. And it's highly correlated to the actual pattern of precipitation sensitivity on the left. This is for the ensemble average, but it holds true for all 5 ensemble members individually. And so in conclusion, the key points are that the PGW simulations show general weakening of orographic influence on total precipitation, consistent with the previous studies I highlighted before. We proposed a simple model that predicts the pattern quite well, given its simple nature. There's potential to use this model with other GCM output and a high resolution precipitation data set like potentially Prism, to get a predicted pattern of alpha without having to run a computationally expensive downscaling simulation like we did for our PGW simulations. And this relationship between alpha large scale and alpha orographic, with the large scale increasing at a faster rate under warming than the orographic scale precipitation, implies a weakening of the orographic influence under warming. Thank you, and if you have any questions, feel free to reach out to me.
Thank you, Matthew. And my apologies. I'm seeing that a number of people have lost the audio, but then a number of us are still hearing the audio as normal. So we will share the recording later today on drought.gov. So yeah, if you have lost the audio, my apologies. Hopefully the recording will perform well.
Okay.
Let me see if there's any questions. Looks like it's back now, the audio, so always something. But thank you, Matthew, so much for the presentation. I don't see any questions for you right now, so I'm going to go ahead and turn it over to Kelsey Satellino for our last presentation, and hopefully the audio will continue to work.
Hi, thanks, Britt. And hopefully you all can see my screen and can also hear me. But I'll keep going regardless, and we'll see how it goes. So my name is Kelsey Satellino. I'm the Digital Communications Coordinator with NOAA's National Integrated Drought Information System, or NIDIS. And I want to take just a few minutes today to demonstrate a brand new feature on the US Drought Portal, or drought.gov, our expanded and improved state pages on drought.gov. So I'm going to share my screen and take you through a very brief tour of one of our state pages, in this case, the Washington state page as an example, and tell you a little more about some of the key features on these new pages and how we hope they're useful for drought monitoring, planning, and communications. So very brief background, NIDIS worked with a team at NOAA's National Centers for Environmental Information in Asheville, as well as state partners, to update and expand the state pages on drought.gov. The goal was to provide a landing page for state drought information that's useful for decision-making, communication, and more, and also directs users to key drought resources at the state level. To access these state pages, users can go to the By Location section of drought.gov from the main website menu and click the State link under Browse by Scale, where you can see drought information at a variety of different geographic scales, or select a state from the Select a State drop-down menu. I'll also point out that the URL for these pages is drought.gov/states/ the name of your state. So that's another easy way to access these. Each of our new state pages begins with some high-level statistics, providing sound bites to help tell the story of drought in your region. We wanted to make sure that all the information on this page was easily accessible for both the expert and the casual user, for reporters in the media and those who are monitoring drought in their region. So we've tried to make this information accessible at a high level, but also provide the ability to dive deeper and learn more about the data for those who are more expert users. So for example, these high-level sound bites provide some quick information, but you can click the Learn More About These Stats link underneath the statistics to open up a page that will provide information about data downloads, the source of all the data, how frequently the data is updated, the last valid date for the data, and more. And this is true for all of the statistics as well as all of the maps on these state pages and other pages on drought.gov. Underneath the statistics, you'll find the beginning of many interactive maps on this page, which I'll talk more about in just a moment. But with all the maps on these pages, this is the US Drought Monitor map for the state of Washington. You can zoom in or out, pan to a specific region of interest, click on a particular county, and clicking that link will take you to the county page on drought.gov, which has additional statistics, data, and maps. Or scroll down, and in the bottom right-hand corner of these maps, you can select the drop-down to select a particular county, which will also take you to the county page, or click the Learn More button to go to the data catalog page for that particular data set which will provide more information on documentation, background, access links, and more. I'm going to talk more about these interactive maps in just a moment, but I want to take a moment to just highlight one of the main new updates to these state pages, which is the addition of this drought overview section and the sidebar highlighting state-level drought resources. We added this section in response to usability testing we conducted, a website survey we launched last fall, as well as website analytics and direct feedback from users and partners. It became clear to us through these mechanisms that many people visit the drought.gov state pages looking for state-specific drought information on drought declarations, water use restrictions, and other local and regional data. These pages get a lot of traffic from curious citizens looking for local information about their area that they live in, reporters in the media, and other drought communicators who take drought information and translate it for decision makers and the public. So our goal was to add this section to help orient those users and direct them to the relevant state drought websites, drought dashboards, state drought plans, state climate offices, and other reliable state resources. I mentioned this before, but the other of the two main features that we've added with these new state pages are we've added a lot more data and maps showing current conditions, outlooks, and more. So all our state pages contain precipitation information, temperature, stream flow from the U.S. Geological Survey, soil moisture conditions, outlooks and forecasts, including quantitative precipitation forecasts from the National Weather Service's Weather Prediction Center, as well as a variety of CPC outlooks for temperature, precipitation, and drought. And an interactive historical time series showing 3 historical drought data sets side by side. I won't go into detail about everything that this historical time series graph can do, but I do just want to highlight that there's a number of features to help refine the data that you're looking at, to zoom in on a particular time period, to isolate a particular percentile category to view it in more detail, learn more about the data set and the legend information, and to download this data in a variety of different formats. You can download an image of the time series graph, or you can download a CSV, XML, or JSON file. And we've added some additional information about interpreting these data downloads as well. Finally, these pages include an additional list of some curated web resources at the state level, including ways to stay informed on local drought information, such as these regional webinars, as well as other key state and regional resources, and ways to submit your local drought impacts. Now, this is a really quick whirlwind tour of one of these state pages. With the last couple of minutes that I have, I just want to hone in on one of the biggest and I think most useful new features that we've added to these pages. And that's the additional customization and interactive options we've added to the maps on these pages and throughout drought.gov. Those of you who are familiar with the website may notice that these maps look a little different than they used to. We've improved the usability of these maps and tried to make it easier for people to find drought information regardless of their level of personal expertise. So for example, if you hover over any of the legends on drought.gov, you will see that a lot of them are now interactive with a pop-up window giving you a little bit more context on some of the more complicated legends. So for example, this map shows real-time stream flow from the U.S. Geological Survey. And if you hover over a particular category, such as below normal, it will explain what percentile of historical stream flow values fall in that below category, with a link to learn more about each of these categories and definitions from the USGS. You can also click on the About tab here, which is hidden behind an accordion, for more information with a plain language description of the map, source information, and our update section includes information about how frequently and when that map is updated. Finally, I want to highlight that this button here, it's a download map icon in the top left corner of every map on drought.gov, allows you to open up a larger version of this map in a pop-up window that will allow you to customize this information. And again, this is true for any map on drought.gov. So our goal is to be able to compare information at a more granular level and to download a high quality image of the map customized to your liking for drought communications. So with this tool, you can adjust the transparency of the layer, change the base map for the map. Of course, you can continue to zoom in or out or pan on a specific region of interest. You can also choose to overlay the US Drought Monitor alongside any of the maps on drought.gov and adjust that transparency as well. And in addition, you can show border outlines for state, county, and tribal land areas. The state and county lines are displayed by default on the state pages, but you can adjust these for the national maps on the website as well. Once the map is looking the way you want it, you can click the Save Map button in the bottom left corner to download a high-quality PNG image. And I'll just highlight one of the other cool features of this map pop-up is that if you zoom in on a region of interest and then go to the Current Data Layer drop-down in the top left corner, you can easily jump between any of the other maps on that same page and keep the same zoom extent, making it easy to visually jump between data sets available from a variety of different sources, jumped to the same exact location for easy comparison. Overall, I just want to end by saying that this update to the state pages is just the beginning. We're always looking for ways to improve the data and resources that we have on drought.gov, the state pages, and the rest of the website. And for example, we're working to add precipitation maps at longer timescales based on feedback from state partners in the Pacific Northwest and other regions. So if you do have questions or feedback on these pages or suggestions for resources that we really should be highlighting, please do reach out to us at drought.portal@noaa.gov, and our contact information is on the website, and it'll be in the webinar summary that goes out via email. Thank you.
Great, thank you so much, Kelsey. Just checking the question box, and I don't see anything. I am going to try, I'll give it another second as I share my screen, and you can see the contact information from all of our presenters today, as well as the date of our next webinar, which is August 28th already. The year is going by very quickly. So thank you to all of our presenters, and mark your calendars for August 28th, our next webinar. And let me take one more look, and I don't see any questions. So with that, we'll conclude the webinar. I do apologize for the issue with the audio today. We will share shortly a recording that will go up on drought.gov via email to all who registered. And so hopefully that recording, you can catch anything you missed. So thank you and have a great rest of your week.